All right, everyone, get ready, because today we're going deep on a paper that could honestly change the way you think about data selection.
Oh, yeah. This one's Unifying and Optimizing Data Values for Selection via Sequential Decision-Making.
Catchy title, right?
It is dense, I'll give you that, but the insights are so valuable if you're working with data valuation or selection.
Especially, I'm guessing, if you've ever felt like your model's performance just plateaus no matter how much data you throw at it.
You're reading my mind. That's exactly who this is for.
Okay, so for our viewers who just want this quick summary, what's the big deal with this paper?
Basically, they've found a way to pick the best data subsets to really boost your model's performance.
Sounds like a data selection cheat code.
Kinda, yeah. The key is they've reframed the whole problem. Instead of treating data selection as this one-time thing, they approach it as a step-by-step process.
Interesting. So you're saying it's more like navigating a decision tree where every choice impacts the next one.
Exactly. And here's the kicker. The paper points out that methods like Data Shapley, the one a lot of us use, are actually based on approximations.
Wait, really? So they've been making assumptions this whole time?
Yep. And this paper lays those assumptions out in the open. More importantly, it explains why those approximations can backfire sometimes, especially with real-world data.
Because real-world data is messy, right? It's diverse and full of overlapping information.
Exactly. And to deal with that, the authors came up with a new method using something called bipartite graphs.
Okay, now you're going to have to break that down for me. What are bipartite graphs and how do they help?
Well, think of it this way. These graphs can capture the complex relationships between data points way better. And that leads to much faster performance gains early on.
Well, that's huge. Nobody wants to waste time and compute on data that's not pulling its weight.
Right. So instead of throwing all your data at the problem, you can use these graphs to identify the most valuable pieces right from the start.
That sounds like a total game changer. Okay, for those of you ready to go deeper, let's unpack the paper's main ideas.
Sounds good. The first thing to understand is that data selection is a sequential process. Every data point you pick affects the value of the remaining data.
So it's like a chain reaction.
Yeah.
Each decision sets off a new set of possibilities.
Exactly. And this paper formalizes that idea by treating it as a sequential decision-making problem.
Okay, I'm with you so far. But how do they model that process? How do they actually represent this sequential decision-making?
They use something called deterministic Markov decision processes, or DMDPs.
DMDPs. That sounds intimidating.
It's not as scary as it sounds. Think of it like planning a road trip where each stop is a data point, and your goal is to find the best route to your destination.
So the destination is a high-performing model, and the route is the sequence of data points you choose.
You got it. And each stop you make influences the rest of your trip. It determines whether you reach your destination quickly and efficiently.
Okay, I like that analogy. It makes it much easier to visualize. Now, theoretically, you could find the absolute best route using dynamic programming, right?
You could. But there's a catch. Dynamic programming is super computationally expensive. You'd have to evaluate every possible route, every combination of data points.
That sounds like a computational nightmare, especially for large data sets.
It can be. And that's where those approximations we talked about earlier come in. Methods like Data Shapley are basically shortcuts in this road trip analogy.
So instead of meticulously calculating the optimal path, they estimate the value of different routes.
Exactly. And that's what we call approximate dynamic programming, or ADP. They're trading off some accuracy for speed and efficiency.
It's like using a GPS that gives you a decent route, but maybe not always the absolute best one.
That's a good way to put it. And here's where the paper gets even more interesting. It looks at how the structure of your utility function impacts the accuracy of these ADP methods.
Hold on, let's back up for a second. When we talk about the utility function, what are we actually referring to?
The utility function basically tells you how much each data point contributes to your model's performance.
So in our road trip analogy, some stops might be more scenic or have better rest stops than others.
Precisely. Now imagine a scenario where each data point contributes something unique and independent to your model's performance.
So each data point brings its own value with no redundancy. We'd call that a linear utility function, right?
You got it. And in that idealized case, Data Shapley and other similar methods would be optimal. They'd perfectly capture the value of each data point.
But as we said before, real-world data is rarely that clean and straightforward.
Right, and that's where the concept of diminishing returns comes in.
The diminishing returns.
Yeah,
So you're
right.
saying that as you add more data points, the impact of each additional point starts to decrease.
Exactly, like adding spices to a dish. The first few pinches make a big difference, but after a while, adding more doesn't change the flavor much.
Gotcha. So how does the paper factor in these diminishing returns?
They use something called curvature, which is denoted by C. It basically measures the degree of those diminishing returns.
So high curvature means there's a lot of overlap in your data. Lots of routes leading to the same destination in our road trip analogy.
Exactly. And that's where things start to break down for those traditional approximation methods.
Because they're not as good at navigating those redundant routes.
Right. The paper shows that their performance actually deteriorates quadratically as curvature increases.
So they become less efficient at weeding out those less valuable data points. And that's where the bipartite graph solution comes in, right?
You got it. This new method tackles the approximation problem head-on by using these graphs to create a more accurate picture of how data points are related.
So instead of making those simplifying assumptions, it maps out the relationships between data points.
Exactly. And what's really impressive is that it does all this while still being computationally efficient.
So it's like a super smart GPS that knows the best shortcuts, but doesn't need a supercomputer to run.
Precisely. And we'll dive into just how well it works in practice in the next segment.
This is already blowing my mind. I can't wait to see how it all plays out in the real world.
All right, so are you ready to see how this bipartite graph method actually performs?
Oh yeah, let's get to the good stuff.
Yeah.
What kind of data sets did they test it on?
They used a good mix of data sets, actually. You know, the kind commonly used in machine learning research. Different data types, different levels of complexity.
So they didn't just pick easy data sets that would make their method look good.
No, they wanted to make sure it could handle a variety of situations.
Yeah.
You know, real world stuff. And the results, well, they're pretty impressive.
Okay, I'm on the edge of my seat here.
Yeah.
What did they find?
One of the biggest things was how much better this method performed, especially early on, you know, in those first few selection stages.
So it's really good at picking out those high-value data points right off the bat.
Exactly. And that's huge, especially if you're working under tight deadlines or you don't have a ton of computing power.
Makes sense. You want to get the most bang for your buck early on. Did they compare it to other methods like data shapely?
Oh, yeah. And it consistently outperformed those traditional methods, especially on data sets with high curvature.
So in those tricky data sets where there's a lot of overlapping information, this method really shines.
Exactly. It's able to cut through the noise and find those key data points that really matter.
I'm curious, were there any specific examples where this method was particularly effective?
Yeah, actually they found that it worked really well on data sets with high feature dimensionality.
So when you have a ton of features to sift through, this method is better at finding the signal.
Right. It makes sense if you think about it. The bipartite graph is designed to capture those complex relationships between data points, so it's perfect for high-dimensional data.
It's like having a super-powered magnifying glass that can zoom in on the most important details.
Now, when it comes to measuring performance, they didn't just look at accuracy.
Right, because accuracy isn't always the whole story.
Exactly. They also looked at things like AUC area under the curve, which gives you a more comprehensive view of the model's performance.
So it's not just about getting the right answer, but also about how confident the model is in its predictions.
Precisely. And in some cases, they also measured how efficient the methods were in terms of computation time.
So how long it takes to actually select the data points. That's a big factor in real-world applications.
Oh, absolutely. And what they found was that the bipartite graph method, while more computationally intensive than those simpler methods, was still significantly faster than dynamic programming.
So it's like finding that sweet spot between accuracy, efficiency, and computational feasibility.
You nailed it. You get the best of both worlds. A more accurate approach without the crazy computational burden.
That's super impressive. But let's be real. Were there any downsides to this method? Any limitations the authors mentioned?
Well, one thing they acknowledged was that building the bipartite graph itself can be computationally expensive.
Especially if you're dealing with massive data sets.
Right. The more data points you have, the more potential connections there are to map out.
So it's a trade-off.
Yeah.
You get more accuracy, but at the cost of some computational overhead.
But they also suggest ways to make it more efficient, like using approximate nearest neighbor search techniques.
So it's not a deal breaker, just a challenge that can be addressed with some clever optimization.
Exactly. And I think there's a lot of room for future research in that area. You know, finding even better ways to speed up the process.
This whole thing has been fascinating. Honestly, it feels like we're on the verge of a major shift in how we approach data selection.
I think you're right. Instead of blindly using all our data, we can now be much more strategic about which data points we choose.
And that could have a huge impact on everything from model performance to the time it takes to get results.
Absolutely. This is just the tip of the iceberg. There's so much more to explore and discover in this field.
Well, on that note, I think it's time to move on to the final part of our deep dive. where we'll explore some of the theoretical implications of this research.
Sounds good. I'm excited to delve into the bigger picture.
All right, so we've seen how well this bipartite graph method works in practice, but I'm curious about the bigger picture. What does this research tell us about data selection from a theoretical standpoint?
Well, one of the key takeaways is the way they formally define data selection as a sequential decision-making problem.
Right, it's not just about picking good data points, it's about understanding how each choice ripples through the entire process.
Exactly. Every decision you make sets the stage for the next one. And by putting this into a mathematical framework, it opens up a whole new world of possibilities for analysis and algorithm design.
So it's not just a practical solution, it's a conceptual breakthrough that could lead to a whole new wave of research.
Absolutely. Now, one of the big questions this raises is how to develop even more efficient algorithms, ones that can get close to the optimal solution without all the computational heavy lifting.
Right, because even though this bipartite graph method is more efficient than dynamic programming, it still has its limits, especially with huge data sets.
Exactly. So finding ways to optimize that process is a big area for future research.
And what about those utility functions? We talked about how they define the value of each data point, but how do they fit into the theoretical picture?
Well, that's another fascinating avenue to explore. You see, different utility functions can lead to very different outcomes depending on the algorithm you're using.
So understanding how those two things interact is crucial.
Exactly. And this paper gives us a starting point by looking at how curvature, that measure of diminishing returns, affects performance.
So the more we learn about these utility functions and how they work with different algorithms, the better choices we can make.
Exactly. It's all about picking the right tool for the job. And this research gives us a framework for making those decisions.
This has been an incredible deep dive. I feel like we've really uncovered some groundbreaking stuff here.
I agree. This paper has the potential to revolutionize the way we think about data selection.
And as data gets bigger and more complex, these insights are going to become even more important.
Absolutely. We need to be smart about how we use data, and this research gives us the tools to do just that.
Well, on that note, I want to thank you for joining me on this incredible journey. It's been a real pleasure learning from you.
The pleasure was all mine. I'm always excited to talk about cutting-edge research like this.
And to our viewers, thank you for tuning in. We hope you found this deep dive informative and maybe even a little mind-blowing.
And if you want to learn more, be sure to check out the paper we discussed. The link is in the description below.
And don't forget to subscribe to our channel for more AI paper deep dives. We'll be back soon with another exciting paper that's pushing the limits of machine learning.
Until then, keep learning, keep exploring, and keep pushing the boundaries of what's possible with data and AI.
We'll see you in the next episode.